Good morning, everybody. I'll start by thanking the organizers for giving me the chance to speak here. The title of my talk is Umbral, Moonshine, Niemeier, Lattices, and String Theory. So this is the outline of my talk. The first part will be review. First, for those of you who are not familiar with this topic, I'll tell you what Moonshine is and what the new development is till 2010. And then the second part will be the new part. I'll be talking about my own research, and both of them will be based on a paper that hopefully will both appear within the next week. So the first part will be the math part, and the second part will be the string part of the talk. Okay, so let's start with the review. So what is Moonshine? Yeah, it's very funny. And for those of you who don't know, this term was introduced into mathematics as to describe an unexpected relation between two types of different structures in mathematics. One is that of the finite groups, and the other one is modular objects. So before I tell you this connection, I might as well first tell you what modular objects are. So for the simplest example is the concept of modular forms. And modular form is simply a holomorphic function defined on the upper half plane that transforms covariantly under a discrete subgroup of SL2R. And what I meant by covariantly is described in this formula where W, we call the W the weight of the modular form. Okay, a famous example of such a modular form is the J function. It is invariant under the modular group SL2Z. In particular, it's invariant under the T transformation and the S transformation. And that is why when you plot the absolute value of this function, you get this beautiful fractal structure on the upper half plane. And string theory is a natural place where modular forms or more generally automorphic forms occur. For the purpose of this talk, let's take a very simple example. So strings means we have a string moving in time, so it sweeps out, the worldsheet sweeps out a cylinder. And you want to compute the partition function of this theory. And the partition function is defined as, it can be defined as a trace over the Hilbert space of quantum states weighted by a temperature and governed by the Hamiltonian. This is the Hamiltonian definition of a partition function. So it makes it obvious that what we'll get is a Q series where Q is e to the 2 pi I times tau. And we also have a Lagrangian way to think about it, and in this way we are instructed to identify the initial and the final time. So in this way our worldsheet becomes not anymore a cylinder but a torus, and we are summing over, we're doing the path integral over this torus. So in this formulation it then becomes obvious that what we will get will be a modular form under SO2Z, because SO2Z is nothing but the mapping class group of the torus. Okay. So more generally, apart from the worldsheet symmetry that, for instance, we just seen, there are also space-time symmetries, and all symmetries have to be reflected in a suitable way in a suitable partition function defined of the theory, for the theory. Okay, so that's about everything I want to say about modular objects, and let's go to the other side, the finite groups. Of course, everybody knows what finite groups are, but the purpose of this talk, I would like to think about them as discrete symmetries of some interesting sub-objects. For instance, the dihedral group can be defined as the automorphism group of some regular polygon. And a slightly more interesting example is when you study the question of optimal sphere packing. So how do you most efficiently pack spheres? So for instance, in 3 dimensions, such a lattice type, a sphere packing, is given by face-centered cubic lattices, and we all know from high school chemistry that this is how copper atoms as well as oranges in the market are stacked up together. And okay, so this is the way I want to think about finite groups. They are symmetries of concrete objects. And now when we have a finite group, we also want to study its representation theory, which is basically a vector space on which this group can act. For instance, in the example of dihedral group, then the defining representation is 2 dimensions because we can represent everything 2 by 2 matrices. Okay. Of course, these are very simple and well-studied examples, and now let's look at some more interesting examples. One triumph of mathematics in the last century is the classification of finite simple groups. And we know that they all fall into infinite families except for these 26 misfits who do not belong to any families. And then they are usually, as we will see later, symmetries of very interesting objects. And the first example is the oldest, the earliest sporadic group. There are 5 mature groups, and the biggest one is called mature 24. And the number of elements is a 9-digit number, so it's a sufficiently complicated object. But even more impressive is the so-called monster, because it's so large. I mean, the number of the element is about the same as the number of atoms in the solar system. So, and the smallest non-trivial representation has 196,883 dimensions. So as you can imagine, it's kind of a fun finite group to be studying. Okay, so that's the introduction about finite groups. Now I can finally tell you what Moonshine is about. As I said, Moonshine is a term that's introduced to describe a relation between modular form and finite groups. Let's start with a classical example, a very famous example, the monstrous Moonshine. The story starts when you look at, again, the J function. We say that, okay, it has this beautiful symmetry, but we can also Fourier expand it near the I infinity cusp, okay, into a Q series. And when you look at these Fourier coefficients, you might discover the Mackay equation, which says 196,883 plus 1 equals 196,884. Okay, great. So what is the meaning? So if you still remember, 196,883 is exactly the dimension of the smallest non-trivial representation of the monster group. And the pattern persists, so these numbers in red are all dimensions of irreps of the monster group. So it is as if the most natural modular function has something to do with the largest sporadic group, which is something that's pretty mysterious, I would say. And this observation was later extended into a full-blown conjecture called the monstrous Moonshine conjecture in a beautiful paper by Conway and Norton. So that's the history of a monstrous Moonshine. And by now, it is a theorem. It's no longer a conjecture. So how do we understand this relation? So my claim is that if you're a string theorist, then you can understand monstrous Moonshine. So why? In order to tell you why, let's go back to the problem of optimal sphere packing. But now we're packing 24-dimensional oranges. And you might ask the question, what is the most efficient way to pack such 24-dimensional balls? And the problem is solved by John Leach in 1967. And that's why the underlying lattice, sphere packing lattice, is called the Leach lattice. And the Leach lattice has very interesting automorphisms. And the study of these automorphisms actually led to the discovery of a few sporadic groups, including the Conway group that we'll talk about later. Okay, but it's 24 dimensions. I mean, what can we do about it? But it's just the right dimension for string theory to study. So why is that? Well, let's remember that the critical dimension of bosonic string is 26. So apart from the light cone direction that basically are frozen, then you have exactly 24 dimensions. So you can consider compactifying bosonic strings on a 24-dimensional torus given by the Leach lattice, and then you compute the partition function of this theory. So from the general picture that I told you about earlier, it's not surprising at all that the partition function has to be a modular form. And in this case, you can show that it is nothing but the J function, the modular invariant that we were talking about. On the other hand, you have also apart, this is just we're using the worldsheet symmetry here. In another arrow, there's also obviously very interesting space-time symmetry, because the symmetry of the Leech lattice will become the symmetry of the torus. And so you study it, as I said, it has Conway as an automorphism group. Well, Conway 1, this is how this group is called. And which is not quite monster, but it's a subtlety. You have to do an actual Z2 twisting, and the symmetry will be enhanced into nothing else but a monster. So in other words, before we don't have the left-hand side, so the connection between the J function, the modular form, and the sporadic group appears to be totally mysterious. But once you put string theory on this in this picture, then okay, worldsheet symmetry gives you one structure, the space-time symmetry gives you another, so it's almost like the most natural thing in the world. Okay, of course, this is not the artist's impression, but physicist's impression of the of the situation. So in order to prove this rigorously mathematically, you have to first to construct the underlying module or the representation responsible for this monstrous moonshine. And then for that, you have to use, people have introduced the concept of vertex algebra and so on. And to prove it, and you have to use the idea of no-go theorem in string theory and introduce the Borges-Kac-Moody algebra. So it's a lot of work, and finally it was proven in '92. And so these are the main contributors to understanding this problem. So that takes us to, let's say, the '90s. And now I'll start with the second part of the review, which will take us to 2010. Okay, but I'll pause for question if there's any. Okay, good. So to understand what's going on in 2010, we will switch gear and remind ourselves something about quantum field theories. So if you have two-dimensional quantum field theory with conformal symmetry as well as at least 2,2 supersymmetry, and the BPS states are counted by the so-called elliptic genus, which is kind of a generalization of a Witten index that transforms nicely under SO2Z by the worldsheet argument I just gave you earlier. Okay, so this is defined in this way, and HRR denotes the Ramond-Hilbert space, and Y and Q, you can think about it for the moment as some formal parameters keeping track of the Virasoro, as well as the U1 are current quantum numbers. Okay, and recall that two-dimensional sigma models with target space being any kth resurface has 4,4 super Virasoro symmetry. So with this argument I just gave you, you can compute the elliptic genus of K3. I mean, it also has a geometrical definition I'll talk about maybe later, but now just stick to the QFT definition. And as I said, it is it is a modular object called the Jacobi form. You can, and it has been computed in the late 80s, and you can write it in many different ways, but I prefer to write it in this way. So mu is some kind of, it's called Apolloge sum. It's some variant of theta function whose explicit form is not important for us. What is important for us is these numbers here. So it has the interpretation that these numbers count the number of highest weight modules of n equals 4 super Virasoro appearing in the spectrum. And it took more than 20 years before these three gentlemen recognized another significance of these numbers, which is the following. So similar to the J function observation, they recognize that these the first 10 Q coefficients are also dimensions of irreducible representations of the largest mature group M24. So if you're interested in the representation theory of M24 in this story, you might just forget about where it comes from and just look at this Q series. You can think about it as generating functions for the number of, of n equals 4 highest Wave modules with a certain quantum numbers. And this whole thing is, as I said, transforms nicely under SO2Z, but we sort of brutally chopped it in half, and it's kind of surprising that this Q series, we get it out in this way, also has a nice transformation under SO2Z. But in order to describe this transformation, we have to extend the idea of modular form a little bit into what we call the Mach modular form. So, you can think about it as a variant of modular form that transforms with a so-called holomorphic anomaly that is controlled by something by a function that's called the shadow of the Mach modular form. And its definition is given in this way, like this. So you have a Q series which is holomorphic. Okay, you have a holomorphic function on the upper half plane, which doesn't quite transform as a modular form, but you can add to it some non-holomorphic integral given by this function S, that is called the shadow, and what you end up with is a non-holomorphic function on the upper half plane, which actually transforms like a modular form. So you trade holomorphicity with modularity. So this modern definition is given by Speicher's, and it was first, the name was first used by Ramanujan, who wrote down examples of the famous Ramanujan thetas, but who didn't give any definition.
Is it a contour integral?
What?
Is it a contour integral?
It's a contour integral. It's from minus. Yeah. Okay, so now we go back to the M24. So after that observation, people want to also formulate a conjecture describing this observation. But in order to formulate a meaningful conjecture, you need also the characters, not just the dimensions. Otherwise, you cannot distinguish between a 45-dimensional ERAP and 45 copies of trivial representation. So for this, you can also consider the twisted or equivariant. These two words mean the same thing for me, of K3 elliptic genus, and again, extract the interesting part. And this H sub G is proposed by computed by 3 different groups, including myself after in 2010 for all the conjugacy classes of M24. So with this Mach modular forms H sub G proposed, now you can formulate a conjecture which says that there exists an M24 module that is infinite dimensional and has a natural Z grading, such that for all the conjugacy classes, its graded character defined in this way simply coincides with the Mach modular form. And in the meanwhile, the conjecture has been proven last year. However, the proof only says that yes, there exists a module, but it doesn't say what type of module it is, so we still don't understand the real origin or the real nature of this correspondence. So that's the end of the review. Again, is there any question? Yeah?
I have a question. Tashikar, Iguchi, and Ogrin identify the series as the dimensions of M24. Does the -1 have any meaning as some kind of degenerate?
No, the -1 you can think about it. No, the -1 is always there. So you can think about it as, you know, some virtual, trivial representation. But anyways, -1 doesn't play any important role. But there's always -1 over there. And for the rest of the coefficients are all positive, and you can quite easily prove that. Okay, so now I'm going to tell you about my new work, and which hopefully will appear next week. And okay, so what we're proposing is that there's a more general framework we call the Umbral Moonshine, and which has this M24 story as one example. Okay, and again, and to be more specific, this Umbral Moonshine is a pattern of relation relating, again, Mach modular forms, and as we have seen in the previous example, and what we call the Niemeier finite groups. So now I'll tell you how we construct, on the one hand, the Niemeier finite groups, and on the other hand, the Mach modular forms. Okay, and then I phrase this Umbral Moonshine conjecture in concrete terms. That will be the plan for this part of the talk. So let's come back to sphere packing. So as we said, if we live in 24 dimensions, and the optimal sphere packing is given by the lattice called the Leech lattice, and there are, given a configuration of such optimal sphere packing, there are special points in the underlying vector space, which I call the dipoles. And the dipoles are, as the name suggests, there are special points in the underlying vector space that has maximal distance to any of the ball in the packing. Okay, so if you can't see these red dots, I'll take off the spheres. So that's how it looks like. And these dipoles also define the lattice on themselves. In other words, the spheres, the configuration of sphere packings define the lattice in this case. And then if you study the dipoles, they also give you a lattice. Okay, so in 24 dimensions, the sphere packing is given by a Leech lattice, and there are 23 orbits of in equivalent dipoles. Okay, they lead to 23 different lattices, and I'll call them the Niemeier lattices. Okay, so there are 24 orbits of the of the automorphism of the sphere packing of the Leech lattice. And I'll call them Niemeier lattice because there's a classification proven by Niemeier in 1973, which says the following. Which says that in 24 dimensions, there are exactly 24 interesting lattices. So it's a coincidence. One 24 doesn't lead to another 24. But my definition of interesting is that the lattice has to be positive, definite, and even, and unimodular. And they are called the Leech lattice, one of them, and then I'll call the rest 23 arising from studying the dipoles of Leech lattice, the Niemeier lattices, and there will be the underlying structure of this part of the talk. Okay, so as I said, I'm going to define from Niemeier lattice some finite groups for you. So the idea is very simple. You have a lattice, and you study the automorphism group of the lattice, and take the interesting part of it, and I'll call that our Niemeier group. Okay, in a bit more details, these 23 Niemeier lattices are specified by the roots, which are spectral vectors in the lattice that has norm square 2 of the Niemeier lattice. And you can easily see that while reflections generated by reflections with respect to these roots are necessarily automorphisms of the lattice. And that is sort of the obvious part, and it sits inside the whole automorphism group as a normal subgroup. So you take that part, you take out that sort of the boring part, and you are left with what we call the Niemeier group. Okay, so in this way, we can construct for each x, when we have 23 such x's, a finite group that we call the Niemeier group. For instance, let's take the simplest Niemeier lattice in the sense that its roots are given by nothing but 24 copies of A1. So the simplest root system you can write down. And its symmetry defined in this way, the corresponding Niemeier group is nothing but the largest sporadic group M24. Okay. So that gives you a uniform construction of 23 finite groups, which we call the Niemeier groups. And now we want to also construct on the other side the Mach modular forms for you in uniform fashion. I'm trying to decide how much details I will go into in this construction. How much time do I have? Half an hour. Ah, okay.
No.
A little less. That's fine. Okay, so let's go into a little bit of details here. So so the aim is that for each of the Niemeier lattices, we associate the Mach modular form, which we'll call HX, via a unique procedure, and which is given by an AD classification. So the first inspiration is this theorem proven by Capelli, Tsiskin, Zuberg, and they are studying the modular invariant combination of chiral and anti-chiral characters of A1 affine Kac-Moody algebras. Okay, so they want to consider matrices, which I'll call NX, such that this combination of left and moving sectors is modular invariant. And secondly, with the normalization that the first diagonal entry is 1, well, corresponding to the idea that you have to have one unique ground state in your CFT, we want to have like only positive definite contributions of left and right sector, also natural from a physical point of view. And the theorem is that these matrices N of X are in one-to-one correspondence to ADE root systems. And M here, which denotes the size of the lattice, as well as the central charge of the CFT or the level of the affine algebra, is simply given by the Cossata number of the root system. Okay. Chi I is here, spin in the last line. Okay. So this is a very beautiful AD classification of modular invariance. And using their results, we can make the same classification on a totally different looking problem. Okay, so this part is really for people who know this kind of modular stuff. So if you're lost, I mean, after 4 slides, you can join us again. So let's now consider a problem regarding the study of Jacobi forms. Okay, so for instance, the elliptic genus I wrote down earlier, they are examples of Jacobi forms. They have 2 variables, a holomorphic function, transformed nicely under SO2Z, basically. So consider vector valued modular form H with n-1 components, such that this combination, the combination between these components of vector value modular form and the theta function here defined above is a Jacobi form of weight 1 and index m. And we want to consider, again, size m-1 matrices denoted by nx, such that this new combination is again a Jacobi form of weight 1 and index n, and again subjected to the same positivity condition. Okay, so it is a different looking problem, but if you go into the technical details, the 2 problems are the same at the technical level. So you can just borrow their theorem and say indeed, there's also a one-to-one ADE root systems here in this classification. So this is a classification on Jacobi forms. So now we want to generalize this concept into what's called the meromorphic Jacobi forms. So these are functions that are no longer holomorphic in the z variable. Z is the log of y, basically. So they have poles in the z plane, which means that they cannot have, a theta decomposition as what we're used to in the Jacobi world. Okay, but there's a very nice theorem. It's by De Boker, Muti, and Zagir last year, which I should say that they refine or generalize the results of Zwegers in his PhD thesis. So which says now we consider such meromorphic Jacobi forms which have simple poles. I mean, they study more general examples, but for my purpose, I want simple poles on the torsion point on the elliptic curve. And we're looking at way 1 objects. And they provide a canonical way to separate this meromorphic guy into the polar part, which I denote psi p, and the finite part, which is holomorphic but no longer Jacobi. Okay, I call it psi f. So this guy who's psi f, which is holomorphic, then we can again theta decompose it. But now this coefficients, instead of being modular forms, will now become Mach modular forms. And the shadow will be given by the theta functions. I mean, we define the theta function. This is the usual theta function defined in the previous page, and we take the y derivative and put z equals 0. That would be a Q series SMI. So it's a canonical object. Okay, so let's now, let's say, I won't give you a detail, but the spirit is to combine their results and the AD classification I showed you before, and using some properties of Jacobi forms, and then can tell you this theorem. So for every ADE root system, now let's consider a weight-half vector-valued Mach modular form with the shadow that's given by, on the one hand, this theta function Sm, this universal theta function that naturally comes out from studying of meromorphic Jacobi forms, combined with the ADE ADE matrix Nx. Okay, so for every root system, we can specify a shadow, specify a weight, and then consider a simple growth condition, which says that it can only have a pole near the infinite cusp at the first component. Okay, this is a vector value thing. And all the other ones have to be bounded, at the cusp. Okay, and then the theorem says that if such a Mach modular form exists, it is unique. Okay, so now we can apply this theorem and apply them and use as input the root systems of the Niemeier lattices and put it into this theorem and look for this Hx. And because of this theorem, if you find it, it's unique. Okay, so in this way, we have a uniform construction starting with the Niemeier lattice to a Mach modular form, vector value Mach modular form. Okay, so this arrow is what I just described in the past 4 complicated slides. So this is the first part of the result. Given any of the 23 Niemeier lattices, on the one hand, you uniquely associate a Mach modular form. On the other hand, you defined a finite group from studying the automorphism of the lattice. And then on the left-hand side, you can also generalize it to associate a Mach modular form for every conjugacy class of this Niemeier finite group. Basically, how you generalize it is to study how this conjugacy class, how these group elements act on the Niemeier lattices, and then you can tweak this arrow to get this. And one interesting thing is that, okay, we have our uniform description and blah, blah, blah. We found these Mach modular forms, and then when you again type it into OEIS, then you find that it recovers actually most of the Ramanujan's example that he wrote down. And another funny thing is that a priori we don't have a theorem saying that this procedure will give you a Mach modular form, because we only have a theorem saying that if it exists, it's unique. But most of the time, if you just plug in an arbitrary ADE diagrams, it just doesn't exist. So it's kind of a miracle that whenever it's one of the 23 guys, it exists. So this is something very mysterious that I discuss a lot with Don Zagier. We don't quite understand right now. So you have this uniform construction on both sides, and now we want to relate the two by phrasing this Umbral-Moonshine conjecture, which says that for all 23 Niemeier lattices, again, there exists an infinite dimensional module of the Niemeier group. Again, has a natural grading such that, again, its graded characters just coincides with the Mach modular forms that we proposed. Okay, and I should say that this is not actually wishful thinking. We tabulated like hundreds and hundreds of, the first few alphas of the representations, and it all seemed to work, but it's not proven in general. Okay.
Multiplicity of all these representations have to be equal to 1 always?
multiplicities of the
representation.
no, and it's an artifact of the first few, right? Because then you run out of ERAPs, then you start to have but there's a lot of stories there, like, yes, indeed, phenomenologically, the multiplicity is always 1 in the beginning, and also the number fields on which these representations are defined has a close relation to the powers of Q that's in the series. It's all very mysterious, and we have no understanding. Not by me. Okay. So that is sort of abstract. So let's again run this procedure again and apply it to the simplest Niemeier lattice. And as I said, in this case, the group is nothing but M24. And you can construct in this way the Mach module form corresponding to the identity element, and it has this closed formula. You can expand in powers of Q as many powers as you want, and yeah, it just reduces the old example. And the next simplest example, okay, now the root lattice is 12 copies of A2, slightly more complicated. And the group from the automorphism is a central extension of the smaller material group M12. And now the vector has 2 components because M minus 1 is 2, where M is the Cauchy number of A2. And then again, you look at the first few coefficients. These are dimensions of the ERAPs of these of the group we constructed, and so on. So to summarize, we have a uniform construction now for 23 incidences of Umbral Moonshine, and I would say that it illustrates a lot the underlying structure of Umbral Moonshine. For instance, in the earlier paper in last year, we observed that there are many incidences of such Umbral Moonshine, and one for each divisor of 24. And we have no idea why divisors of 24 and so on. And now we understand because we were just observing, we were just discovering the pure A series where the root lattices has no D and E components. And then it's kind of from hindsight miracle that we got the groups right because we are just doing experiments and we have no uniform construction whatsoever. I mean, almost uniform, but no, we didn't understand. And now we know that these are pure series, pure A series, and now we know how to incorporate the D and E series. So that's pretty satisfactory to myself, at least. But the question remains. For instance, you can go about to prove the Umbral Moonshine conjecture as I just phrased it. Basically, you have to extend the technique of Terragannon, or also has been used before by other people in other contexts, to these more complicated vector-valued Mach module forms, but it still would not give any insight of like the core question, like how to understand it and what the representations are, what the underlying module is, and a related question is that you see, I mean, after you derive the Mach module forms, and on one hand, and the finite groups on the other hand, using Niemeier lattice, you can throw it out and say these are groups, these are the relations. But I mean, we see now that Niemeier lattices really play a central role. So what is the role of Niemeier lattice in the construction, in the understanding underlying representations? That's also unclear. So a related question is that maybe the success of monstrous moonshine can be repeated. We can have a physical or even geometrical context for this moonshine that will help us to understand it. So that is the end of this part.
Analog of K3 for this.
Yeah, that's a very good question. I mean, it's closely related to what I'm going to say now. Not quite, but yeah. So how much time do I have?
17 minutes,
18 minutes. Oh, I have plenty of time. Yes. Okay. So the last part will be the string part of this string math talk. And so just it's a natural question left from the previous part. What's the relation to string theory? And I don't have a very satisfactory answer, but now let's just explore together. So let's go back to the M24 example. And at the level of numerical evidence, right, it was discovered in the context of elliptic genus of K3. And let's recall that elliptic genus is a Witten index receiving only contributions from the BPS state. So it's computing not computing only the Q cohomology of the spectrum, but not the whole spectrum. I mean, there are parts of HRR, that the Hilbert space, that it doesn't know. And in particular, it is rigid. I mean, it's the same for all K3 surfaces. I mean, a way to understand it is that there's an alternative. Well, it depends on where you're coming from to call which one alternative. But there is another definition, purely geometrical, of the elliptic genus, and which phrases that as a topological quantity, generalizing, for instance, the Euler characteristics, signature, chi-y genus, and so on. So it makes it clear that it's a rigid quantity. Okay, so it seems that this seems to suggest that M24 might have something to do with K3. So a most naive guess is that, okay, it wouldn't be a mystery, at least not as much, if there exists a K3 surface corresponding to one point in the moduli space that has M24 symmetry, right? Because it's a rigid quantity, so as long as you find one point having this symmetry, you're done. But unfortunately, the answer is known. One way to see it is a theorem by Mukai, which says that all finite group symmetries of K3 surfaces that preserve the hyperscalar structure are subgroups of M23, so it's simply not big enough. It's never big enough. And if you're a string theorist, you might say, haha, that's because you're not a string theorist. That's too stupid. I mean, because we are computing the sigma model quantity, and sigma model has more symmetry than just the classical symmetry of K3. So maybe there is a K3 sigma model whose symmetry necessarily contains the symmetry of the underlying K3, the target K3, and the symmetry might be big enough to cover M24. That's a very reasonable guess, but so inspired by this observation between K3 elliptic genus and M24, the three gentlemen has studied this problem, and they concluded that there exists no sigma model of K3 whose symmetry is M24. And also, there are K3 sigma models. They're invariably sort of the orbifold models whose symmetry is not even contained in M24. So it's too big and too small at the same time. Okay, so that's depressing. So you might conclude that it might be maybe this is just a numerical coincidence. But I have to stress that this is not in contradiction to the idea that M24 acts on the BPS spectrum of K3 sigma models, because having a symmetry group acting on the K3 sigma model is sufficient but unnecessary condition that acts on the BPS part. Okay, so it's like, you know, it can have enhanced symmetry when you only look at the cohomology of the space. So, but okay, so it's kind of mysterious how to proceed from this point. If any of you have good ideas, you should tell me. So it might be a coincidence, but on the other hand, as I mentioned earlier, there's a lot of evidence from study, not just the elliptic genus, but equivariant elliptic genus, when you do have explicit finite group symmetries of your sigma model. Then the equivariant elliptic genus you compute in this way are always compatible with the assumption that M24 acts on the BPS states. Okay. And moreover, you can also look at not just perturbative strings, and you can also look at non-perturbative. At the non-perturbative level, you can look at the full, let's say, full string theory compactification. And for instance, in this setup where you have type 2 strings on K3 times T2, then the half as well as the quarter BBS spectrum all show hints, again, numerical hint relations to M24. So maybe it is, after all, too many quote-unquote coincidence for this connection to be a red herring. So yeah, obviously there's still a lot to explore and to see what is really going on. And so now I'm introducing this third corner of the triangle that we want to establish, which is the relation between Moonshine and K3 surfaces, K3 compactification of string theory. Okay, and it is one motivation is, of course, to understand Umbral Moonshine, what is really going on between this mysterious connection between two mathematical objects, but it is also important for string theory on its own, because as we know, as all the string theorists know, K3 is ubiquitous. So, for instance, it features in the duality, in the web of dualities, and then it is also led to many important achievements of string theory, including the Schrödinger-Waffa black holes, and also one of the first examples of ADS-CFT of Malesheim. So if there are some hidden quantum symmetries you would like to understand it and understand what the consequences are for string theory. So that's the motivation. So let's just try. And so this is based on work with the same authors as before, as well as the Stanford group, including Shami Katru, Shi Dong, and Tim Gaza. And for those of you who are going to strings, I mean, Shami is going to talk much more about this than I do. So let's now consider a more general setup, which is consider heterotic strings on K3 times T2, because it is sort of the most, it's still under control because we still have 8 supercharges, and we have a lot of room to play with because we have the gauge bundles from the heterotic strings and so on. So let's study if we can find M24 there. And let's remind ourselves, when you have when you consider EA times EA heterotic strings on K3 times T2, and from the anomaly consideration, the instanton numbers on two sides of E8 has to add up to the Euler characteristic of K3, which is 24. So we can parameterize the topological sector of such compactifications by this number n, denoting the instanton numbers. And the heterotic type A, type 2A duality then says that the dual theory will be type 2A string theory compactified on a Calabi-Yau threefold, which is an elliptic vibration over the Hitzelsbruch surface. And exactly which Hitzelsbruch surface then is given by the instanton number over here. So this is developments from the late 90s. Okay, so we want to work in this setup, explore this setup, and I can tell you what we have been doing so far. So the first quantity we're interested in studying is a simple worldsheet quantity from the heterotic side, which is the new so-called new supersymmetric index, and that is closely related to threshold corrections. Maybe you still remember from Boris' talk. Okay, it is defined in this way. So this actual factor of 1 over eta squared, where eta is the Dedekind eta function defined here, is just it's just taking care of the non-compact direction. So for an internal CFT, we're interested in this in this trace over the Hilbert space, over the Grammont-Hilbert space. Okay, and this guy factorizes because we have basically because we have T2 times K3. It don't completely factorize. There's some relation between, you have to fit the boundary conditions and so on. But nevertheless, the results will be factorized into a theta function of T2, which we don't care so much about, and a factor that comes from K3. Okay, by a factor coming from K3, I mean that the factor coming from studying this CFT with central charge 20, 6. Okay, so the right mover has 6 coming from just the K3, and then the 20 contains the 16 of the gauge bundle. All right, and we want to study again in different instanton sector. And the most well-studied example of this is the so-called standard embedding, where you just embed the K3 spin connection into one of E8 and have the other E8 totally unbroken. And the instanton number, of course, is then 24, 0. And then in this case, by a worldsheet argument, you can relate what we defined earlier to the elliptic genus of K3. So after some rewriting, you can get this answer given by the Dedekind eta function I just wrote in the previous slide, as well as E4 and E6. So which are just the Eisenstein series that generates the ring of modular forms. And you can rewrite it from the relation to elliptic genus. You can rewrite it in this way. So this ZS and Z0, there are some Q series given by, again, n equals 4 characters that I'm not going to write down. But it suggests that, okay, M24 might have an action on this theory as well, on this spectrum. Which is, okay, after all, not surprising, because for the standard embedding, you know the spectrum is exactly related to the spectrum of the K3 sigma model. But how about other embeddings with other n? So the first thing we realize is that, well, it has been mentioned before in the earlier literatures in the late 90s, I have to say, is that, but you can prove this rigorously using an argument based on the properties of modular forms. More specifically, the only weight 10 modular form is given by E4 times E6. Okay, there's a typo. That's fine. That's fine. E4 times E6 up to a multiplicative constant. Then you can prove that the above result, the result for this K3 factor in the new supersymmetric index is actually universal, although the underlying CFT is so different. Okay? So universal so you can again rewrite it into n equals 4 characters and have this M24 related mock module form showing up. So you might wonder about the possibility that M24 acts on this much more general class of the theory. But let's leave that for later. On the type 2A side, you can also argue for universality. And it's kind of the simplest consequence of the relation between topological strings on Calabi-Yau threefold that are elliptic fibered and quasi-modular forms. Okay, so this is analyzed carefully in some paper in 2011 by many authors, including Mughal over here. So on the 2A side, basically, it's the same argument, and you get the same universality result. So as I said, you might wonder about the possibility of having an M24 action, but it is a little bit too much, to speculate if you don't have any more evidence. So as evidence, we explicitly computed there's a G missing here on the right-hand side. There should be a G insertion. You can again compute the twisted new supersymmetric index explicitly. Once you can realize this symmetries explicitly, for instance, at the orbifold point or at the Gepner point, and then you can compute it. And again, you find that for many of the symmetries we found, well, they're again consistent or indeed coincide with what's predicted by the assumption that M24 acts on it. And as I said, it wouldn't be surprising in the standard embedding case. But what is very surprising for me that it also seems to work. Well, it just works on the nose for the non-standard embedding cases. So, which is a priori have nothing to do with the elliptic genus. Okay, it has different supersymmetry and so on. So this is something that we will refine on later. And so what is the dual on the dual Calabi-Yau? Then it suggests like if you accept the assumption or the speculation that's motivated by this twisted computation, the M24 axon, this spectrum of the CFT, then it suggests an M24 interpretation of the genus 0 Gromov-Witten invariance on the Calabi-Yau side just by a string duality. And moreover, you can, with a similar consideration as before, you can generalize it to the higher genus Gromov-Witten invariance. So on the heterotic side, you will be inserting more graviphoton in the computation. Okay. And also more general cases. I mean, all these cases we only have Q. We only have one variable which corresponds to the fact that we're turning off all Wilson lines, and you can turn on Wilson lines, and you still see pretty interesting structures. Okay. So one thing I can say from these experiments so far is that the interesting symmetries seem to be even more prevalent than naively expected. Okay. Obviously, there's still a lot that we have to learn, and especially the natural question is, what about the other cases of Umbral Moonshine? There is 22 other cases, and actually, for me myself, that was one of the biggest motivation to turn to heterotic string compactification, because it has enough central charge to consider the possibility of relation to a Niemeier lattice and so on. But that much we haven't really explored. I think that for that you definitely need to turn on Wilson lines, but that's too much of speculation. I don't have anything concrete to report on that right now. So that finishes my talk, and please join us in Paris for String Math 2016.
In the work of Terry Kahn, that talks about natural operation on lattices, which is called bluing, so you can take simple lattices and do bigger ones. What is the meaning of this, or do you have any idea what it could mean for modular forms? Is there some ring-like structure?
That's a very good question. Well, I'll make, okay. The question is, there's something called the gluing procedure of you glue different lattices into a bigger one that I think was first developed by Nikulin. And Terry Gannon, in his paper in which he proved this M24 conjecture, he mentioned this connection. And the question was like, could that imply some interesting structures among the Mach modular forms? Okay, so I'll make two comments. One is tangential to what you say. So first, there is a discussion again by Nikulin recently in last year or something, where he in a different context he just studied Kähler K3s. So he abandoned like the assumption of the K3 has to be algebraic, and then and he studied the automorphism on the lattices of these Kähler K3s, and then he showed that you need from this gluing procedure, you can glue them into all Niemeier lattices. So his slogan is that all Niemeier lattices should play a role in the study of K3 automorphisms. So that's a tangential comment. Then the second one is, indeed, I'm very interested in such a structure. Again, in the different constructions, different gluing constructions of Niemeier lattices, because we do observe a lot of multiplicative-like relations among different Mach modular forms that we have constructed, which again we don't understand, and that should come from some structure, as you said, among the Niemeier lattices, and we should also have implications on the underlying representation.